Alright, so we're going to look at actually finding the area under the curve. And what we're going to do is we're going to use this idea of making a bunch of little rectangles. Okay, and we're going to add up all the areas of our little rectangles. And we're going to use uniform rectangles, meaning they're all going to be the same width. And so what we're going to need to do is we're going to need to find the area of all these little rectangles. Now, in order to do that, we're going to need to know the width and the height of each rectangle. So, let's say this is my function, this curve here. Okay, so this curve is my function. So it's f of x. And I've got all these rectangles. And I'm trying to find the area under the curve between points A and B. So from A to B. Each rectangle has its own area. If I break this area A to B up into n rectangles, so I've got a total of n rectangles. That means each little rectangle is going to be B minus A, okay, because that's the total length of this segment, okay, that's the length. I'm dividing it into n segments. So each little segment is going to be that total length divided by the number of segments that I've made. That is going to be the width. The height, okay, the height of each rectangle. So let's look at this rectangle right here. Okay, the height of this one is determined by where I make the endpoint. Okay, because when you're making rectangles under a curve, you have two choices. You could use the right side of the rectangle to make your height, or you could use the left side. That was the left side of your rectangle, or here you could use your right side of your rectangle to determine how tall your rectangle is going to be. And you can use either method when you're doing this. I'll go through both ways, but majority of the time it's going to be easier to do it if you use the right endpoints to make the height, and I'll show you why. As I'm going along, okay, this would be the first rectangle, here would be the second, and this is the third rectangle. If I'm using left endpoints, this first rectangle, okay, is b minus a over n wide, and it's this tall, okay? Now this is a, so it's a tall. The second rectangle, so this is the first rectangle, is a for height. The second rectangle is going to be a actually I should here. It's not a tall, it's the function at a. So it's the function at a tall. This next one is going to be the function. Okay, so its height is the function. Okay, because these are function values. These are f values. So it's as tall as the function evaluated at this point, at this x value. Well, this x value is a plus one of our widths. So if I evaluate the function at this, okay, at this x value, this is how I would do it. I would take a, I would add one width. So for the second rectangle, I'm adding one width. For the third rectangle, for the height of the third rectangle, I would be taking a and adding two widths. So I'd be taking b minus a over n times 2. Because I'm going from a, I'm going over 1, 2, Okay, and that determines how tall my third rectangle is. If I keep doing this for the ith rectangle, it's going to be the function at a plus the I minus 1. Okay, it's always going to be, it's one less than the rectangle I've got. So the ith rectangle, its height is going to be the function evaluated at a plus the width, okay, times I minus 1. Okay, because for the third rectangle, I multiplied it by 2, which is 3 minus 1. For the first rectangle, I multiplied the width by 1, which is 2 minus 1. So using left endpoints, we're going to have to introduce this I minus 1 term, which makes it more complex. Let's look at what happens if I use the right endpoints. Okay, so here I've got the same picture, only this time I'm getting more rectangles in here. My width is still going to be the same. I'm still going to be taking b minus a and dividing it into n rectangles. That's still my width. My height now, if I look at, let's say this is my, well, these are still left endpoints, but here's my curve, and then now I'm doing right endpoints. So my first rectangle, I'm going to use the right side of it to determine how tall it is. The right side. Right side. Okay, so these are right endpoint rectangles. Okay, so let's say this is A, and this is B. Well, the height of my first rectangle, this is the first one, is going to be the function evaluated at A plus one of my widths, because this value right here is the one. So it's A plus one of my widths. So times 1. That's the first rectangle. The second rectangle is going to be the function evaluated at A plus 2 of these widths, because I'm going over once, twice. And I'm evaluating the function at that value to get how tall it is, to get this height value. So it's b minus a over n times 2. So for the ith rectangle, you see this one's going to be better because 2, 2, 1, 1. The ith rectangle is the function evaluated at a plus I widths. So b minus a over 2 times I. And I don't have that I minus 1 term. That makes things more complicated. Okay, so that's how you find the height. So I've got width times height of each rectangle. So in order to find the area, I want to add up, okay, the areas, the area being width. This is width times the height. I'm going to use right endpoints because that's easier. So here's the height. The height is the starting value plus the width times I. Okay, the function at that value. And I want for all of the rectangles from the first rectangle up to the last rectangle, the nth rectangle. So I'm adding up all the areas. This is area because it's width times length, or width times height, base times height, whatever you want to say. So I'm going to add up all these areas rectangles. But I want to find out what the area is getting closer and closer to as I get more and more rectangles, because if you can see here, this picture, okay, my area is going to be close, but I'm going to be overlapping by this much. I'm going to have these little corners are creating more area than I actually need. These pieces here where I'm missing I'm missing some area, so it's not the best representation. Here, down here, I'm a little bit closer. because I've got more rectangles, and I'm losing more there, or I'm losing less. I'm overestimating less here, and I'm losing less there. Okay, for a drastic change, compare this to if I just use 2 rectangles. Okay, so there's 1 rectangle. There's 2 rectangles, okay? I would be off by a lot because this is too much and that's missing. So they kind of counteract a little bit, but the more rectangles I have, the closer I'm going to be to the actual area. So I want to take the limit of this as n goes towards infinity. As I start to get an infinite number of little rectangles, I want to see what my limit of my area, of the sum of all the areas of these rectangles are. This is a Riemann sum. Okay, it's also the first way that was developed to find the area underneath any curve accurately. And this led into definite integrals, which is what we'll learn after we learn this. Okay, so I'm going to do an example to show you how this really plays out. So I've got a function that's going to make a curve, x squared plus 1. So I'll just graph that. So it's a parabola, and it's shifted up 1. So my starting point here, I go over 1, I go up 1. Over 2, I go up 4. Over 3, I go up 9. Okay, and I want to find the area of this between 0 and 3. So I want the area. So here's my curve. And I want to find the area in this region. Okay, so what I would do is I'd fill those up with a bunch of little rectangles, okay, and I want an infinite number of rectangles in there. So I'm going to set up my Riemann sum using right endpoints, okay, because right endpoints, I don't have to worry about that I minus 1 term. So my Riemann sum, I'm going to take the limit as my rectangles approach an infinite number, okay, of the sum, so I'm going to be adding up all the areas of my rectangles as I goes from the first rectangle up to the last rectangle. Okay, and I want the width. The width of each little rectangle is going to be, okay, I've got a total length down here. This is 3 long. I'm going to take that distance of 3 and divide it into n rectangles. So my width is 3 divided by n. So that's the width. My height is the function evaluated at my start point, which is 0, okay, because that's the first point I want, 0, plus my width times I. Okay, so if I pick a random rectangle in here, let's say it's this one. I'm using right endpoints. Okay, this is my ith rectangle. I've had, okay, there's been a bunch of rectangles coming up to this one, but this is the ith rectangle, and its height would be I widths away from my start point. Okay, each little one here is 1 width, which is the value 3 over n. I've had I 3 over n's to get to this point. So this point is 0 plus 3i over n. If I plug that x value into my function, that's going to spit out this value. This is the function evaluated at 0 plus 3i over n. So that's the height of my rectangle. So now what I want to do is instead of having this f, I want to use my actual function. So I want the limit as n approaches infinity of the sum as I goes from 1 up to n of my width times my function evaluated at this number. I really don't need the 0 because I'm adding 0 to something. So I just need the function at 3i over n. So that means I'm putting 3i over n in for x. So I'm going to have 3i over n squared plus 1. Okay, and that's my function at that value. So let's simplify some things in here. I'm going to square this out. So we get 9i squared over n squared plus 1. Now this 3n, that would be a constant. And so what I'm going to do, because n is just a number, okay, that's how many rectangles I have. It's a constant. So when I take 3 divided by n, that's still a constant. And I can take that and move it out to the front of my sum. So that's what I want to do. Now I've got the sum of these things. Sums are just like derivatives. I can give them to each term. So I'm going to give each one of these terms their own sum. So since I'm giving them their own sum, and this sum here has a 3 over n in front of it, that means when I distribute, okay, I'm basically distributing this. So both of these things are going to get distributed to both terms. So this guy here, 9i squared over n squared, gets its own sum with the 3n. I also give the 1 its own sum with the 3 over n. Okay, now I've got constant values here. Okay, the 9 and the n squared, so 9 over n squared is still a constant, so I'm going to bring that out front. So if I take 9 times 3, I get 27. If I take the n squared out, which is on the bottom, it's going to go on the bottom with this guy. So I've got that summed from 1 to n, and now it's just I squared. Here I don't have any constants, so this will stay the same. Now we're going to use our summation rules to change these sums into expressions with n in them instead of i's. So I've got, give myself a little more room here. The limit as n approaches infinity. Okay, I'm going to have the 27 over n cubed. Now the sum of I squared as I goes from 1 to n is n plus 1, 2n plus 1 over 6. So multiplying those things together. I'm adding that to 3 over n times, okay, remember the sum of a constant is just that constant times n. So this is just 1 times n, which is n. Now if I start simplifying, okay, I can reduce the 6 with the 27. Take a 3 out of both, that becomes a 9. This becomes a 2. I'm actually going to multiply this top part out. So here I would have n squared plus n. And if I multiply that with this parenthesis, I'm going to have n cubed, sorry, 2n cubed plus n squared plus 2n squared plus n. Okay, so now this is over 2, and I've got the 9n cubed over here. Here my n's will cancel, I'll just have a plus 3. If I continue to simplify, these will come together and become 3n squared. So I'm going to have 9 over n cubed times 2n cubed over 2. Okay, I'm going to split this up. I'm going to give each term its own denominator here. Times actually, let's hold off on splitting it up. plus 3n squared plus n. I'm going to combine these things. So on the top, this 9 will distribute to all three terms. And on the bottom, the 2 and the n cubed will just kind of mash together. So I'm going to have 18 n cubed plus 27n squared plus 9n. Don't forget my plus 3 that's over there. Now I'm going to give each one its own denominator. So I've got 2 and n cubed. That goes underneath each one. I'm still evaluating the limit as this thing, as n approaches infinity. So I'm going to keep simplifying here. Okay, n cubes will cancel, and this is just 9. Here, I can keep the 27 too, but 2 of these n's, so these 2 n's will cancel and leave just 1 on the bottom. Here, this n will cancel and make this a squared. Now I can evaluate my limit. So remember, when I'm taking the limit of a sum, I'm taking the limit of each piece. Okay? So this piece, the 9, as n goes to infinity, there's no n here. So that's not going to change, it's going to stay 9. Here, as n goes to infinity, I have 27 divided by a massive number. So if I take 27 divided by some huge, huge number, it's getting closer and closer and closer to 0. In fact, the limit as we approach infinity is 0. Same with this term. I've got 9 divided by some huge number, which is basically 0. And I've got plus 3. So when I add these together, I get 12. And that is the area under the curve from 0 to 3. So if we're talking inches, if our units are inches, this would be 12 inches squared. And that's the process for finding a Riemann sum. It's long, it's lengthy, but if you stay organized and write out your steps step by step, you won't get lost, and you'll be able to follow your work. If you do get a weird answer, you'll be able to go through it and check and see where your mistakes are. So keep organized. It also make it easier for me to find your mistakes if you have them, or to grade your work as you're doing it.